All right, well, thanks for coming back, everyone, for my second tutorial. Okay, so I put as I promised, the last one on my website. So if anybody had any trouble finding it, if you happen to look for it, let me know. This is a quick recap of what we covered of the highlights from last time, right? So our interest is in this theorem, which is a theorem in topology, but now this is a formal pi1-2 statement in second-order arithmetic. Again, we're thinking of these sometimes as problems. So what does this say? GS has every infinite CSC space where we have this particular coding representation of countable second countable spaces in second-order arithmetic. Every such space has an infinite subspace that is indiscrete, has the initial segment topology, final segment topology, is discrete, or has the cofinite topology, right? One of those 5 options. And we saw the classical proof, and we're going to return to that classical proof shortly. But then alongside it, right, as a kind of foreshadowing of what's to come, we've now also looked at 3 combinatorial states. So these have nothing to do with topology. Here, of course, is Ramsey's theorem for pairs. Every coloring of the pairs of integers with 2 colors has an infinite homogeneous set. And then we have these 2 order principles, CAC, chain any-chain principle. If you have a partial order, has an infinite chain or anti-chain. Ascending, descending sequence. Every linear order has an infinite ascending or descending sequence. Okay, so now we can carry on with where we want to go. And so where I want to start is now to look back at that original proof and just make sure that that proof can be carried out somewhere. And the place where it can be carried out is ACA naught, right? And that's not so surprising. A lot of these kind of constructions can be carried out there. So, but now let's do it formally, right? So we're arguing in RCA naught now. So now we have a CSC space, and I'm just taking the domain to be the natural numbers. And here are basic open sets. And then the key is, right, remember, if you remember back to that original play, the first thing we did was we defined a certain kind of equivalence relation using the closure operation on points. Well, the closure operation we can define using arithmetical comprehension, right? So there it is. So we have this closure operator. You know, it's a set of pairs x, y, so that informally x is in the closure of y. That's what we'll write. And now that we have that, we can go ahead and do the proof, right? The proof that we had before. We define our equivalence relation. That's delta 1 using the closure operation, so there's no issue there. We repeat the argument. If there's an infinite equivalence class, we're done. Otherwise, we can pick representatives, and now picking representatives is not hard, right? Because we can compare elements using the closure operator, so we can do that actually in a delta 1 way. We can pick representatives out of everything, so that no 2 elements are both in the closure of the other. Okay, so I'm going through this fast because I'm referencing the proof from yesterday. Hopefully this is somewhat familiar. And then, therefore, from that we can define this ordering relation less than, right? Again, that involved only the closure operation. All right, what do? We say, okay, apply CAC. If there's an infinite chain, then we're done, because now it's looking like indiscrete topology. If we're in the initial segment topology, right? If there's an infinite chain, we apply AD. We apply CAC. If we get an infinite chain, we apply ADS, right? Both of which are consequences of Ramsey's theorem for pairs, as we discussed last time, which is itself provable in ACA naught, right? So all of this is happening in ACA naught. And if we have the infinite anti-chain, then we're in this T0 case, and that's the situation now where we're in the T1 case. That's where we now have the argument from the end of the talk last time, where we're now doing this inductive construction of a discrete subspace, right? So rather we say, if there's an infinite subspace with the cofinite topology, we're done. If not, then we do the inductive construction from last time. Yeah? And the inductive construction just was what? It used this assumption that no subspace has the cofinite topology, and therefore it used the fact that if you give me any subspace, any infinite subspace, I can find a neighborhood, an open set, which has non-empty intersection with it and infinite complement, right? So I have to ask some questions about, is this infinite, right? Okay, so that's some pi2 questions uniformly in what's going on. So ACA naught can, of course, do that. Yes, Anton. Yes, but it's absolutely true, except for the fact that I can also just do it then with the basic opens, right? So because I know there's an open with this property, there's a basic open, so I can in fact just search through this. So I don't even have to enumerate the open, right? Yes. Any other questions on this? So this is completely provable in ACA knot, right? That's our upper bound. Okay. Okay, so now what we're going to do is we're going to do a thing that's very common in reverse math is we're going to take this principle and we're going to break it apart into a bunch of variations, right? And we don't do that solely because we like to have a lot of different principles, although that's also part of it. But we do it because if you do it right, these variations should somehow be, shed some light on what you're studying, right? Okay, so here are the versions that we'll do. So here's just a statement of the full GS. And then let's look at the following version. So first one is WGS, where we're going to do the same thing, except we're going to combine, we're going to merge these last two possibilities, discrete and cofinite topology, and we're just going to say T1. Okay, so it's now saying it has a subspace which is indiscrete, initial segment, final segment, or T1. Right? So that's WGS. We'll call that weak GS. Then we'll have GST1, which is like the complement of that, right? It's GS, but solely for T1 spaces. So it's of course just going to say every T1 CSE space has a subspace which is discrete or cofinite, right? Can't be any of the other three if you're a T1 space. Okay? And then we can sort of, for technical interest, also look at versions of both of these, WGS and GS, where we decorate with the CL superscript, where we mean that, okay, the input or the problem, or the instances are not just an infinite CSE space, but an infinite CSE space together with the closure operator on points, right? Which is, right, required a jump to, or one quantifier to define, right, in the previous slide. Okay. All right, so how do these correspond, right? I said that hopefully this will somehow be illustrative or try to sort of helpful in understanding the proof. And so we can kind of see where these things line up with respect to the elements of the proof we just saw. So here's the full Ginsburg Sands theorem, of course. Here's GSCL. So you can think of that as whatever the strength of this is, morally speaking, it should be the strength of the Ginsburg Sands theorem. But if you delete any complexity that arises out of having to define that closure operator, right? If that's elevating the complexity of the theorem at all, now that's gone away. That's kind of how I would think of it, right? Here's the weak GS. So that's the same thing, but you forget about the whole inductive construction at the end that handled the T1 case. Yeah, so that's now gone. WGSCL, forget the complexity of the inductive case and forget the complexity of building the closure operator. And then GST1, that's just the complexity of handling that inductive construction at the end, right? How complicated was that inductive construction? That's kind of the way to think of it. Okay, so in somehow these principles capture the various sort of different chapters of that proof, right, as we outlined in the talk. Okay, so let's start right here, and let's think back real quick to what happened here. So remember that sort of, if we had the closure, we defined this tilde, this equivalence relation, right? We said, okay, let's suppose there's not an infinite equivalence class. Then we defined this partial order, right? And then we did what? We hit it with chain any-chain, right? And in the case of a chain, we hit it with ADS, ascending-descending sequence, right? And ascending-descending sequence, I gave you this as a little exercise at the end of yesterday, right? RT22, Ramsey's theorem for pairs, implies chain any-chain, which in turn implies ADS. So both ADS and CAC are consequences of CAC, yeah? And so the kind of non-trivial combinatorial things we're using in the proof, in the part of the proof corresponding to this, is CAC. That's the way to think of that, right, that we saw. And in fact, right, we can show that that's exactly the right level, right? So this is a nice way, I think a nice example of where that breaking up really sort of sort of highlights the necessity and the sufficiency of a certain principle. So this principle here is just CAC, right? Over RC naught, they are the same. Okay, so let's go through this proof. I think it's a nice proof. Okay, so how do we get WGSCL from CAC? Well, that's the proof we already saw. Right? That's the proof. Again, using just the fact that also CAC implies ADS. I do that. Remember, WGSCL doesn't do the inductive construction at the end of the T1 case. It just reduces to the T1 case. So our interest is in the reverse, okay? All right, so here's a partial order. Let's suppose there's no infinite anti-chain. We're going to build an infinite chain. All right, so here's what we're going to do. We're going to define these kind of, let's think of them as sub-basic open sets, or it's going to be a sub-basis, so they might, not necessarily closed under intersection. But VP is just going to be all those things that are larger than P in the partial order, above P. And okay, so this gives us a uniform sequence of these VPs, and in a delta one way, we can close those off under intersection and generate a CSC space so that we actually have a basis. That's very easy, right? Just kind of generate the CSC space out of these sets. Just have a specific U sub n where that n stands for the intersection of these finitely many sets, right? So that's all right. So first claim. So P is in the closure of Q if and only if Q is above P, right? And that's it's not hard to see. So first, if P is in the closure of Q, then every open set containing P contains Q. So Q is in particular in here, right? So Q is above P. And if P is not in the closure of Q, well, then P belongs to some open set that doesn't contain Q. So let's say P is in VR, and Q is not in VR, right? So these all come from intersections of these sub-basic open sets. Then that means this R, whatever this R is below P, but not below Q, so P can't be below Q. We have this. And so what do we have, right? This is given to us, and so we can define the closure just in terms of this partial order. That means the closure exists. That makes sense? Right? This proof is happening in RCA not, right? Now we have the closure. And in particular, that means that this CSC space that we defined here can be viewed as an instance of WGSCL. Right? It's a CSC space with the closure operator. All right. So let's hit it with WGSCL, and we get an infinite subspace Y of P. Okay. There's no infinite antichain, so Y is not an infinite antichain, right? That was our assumption. And so we can pick 2 points that are distinct, right, and comparable in this Y. So what do we have here? We have that P is, by what we noticed with the closure operator, P is in the closure of Q. Okay? And P is not above Q, so P is not in U sub Q in that particular open set. Okay, so from those two facts, right, we can conclude that Y is neither T1. In a T1 space, you cannot have such a situation. And it can't be indiscrete because in such a set, you cannot have this situation. Make sense? Okay, so that means that, right, what WGSCL returned, it either returns an indiscrete, a T1, or a final segment or an initial segment. Right? Those are the 4 possibilities for the weak case. Okay, so let's suppose it's the initial segment topology. The final segment topology is exactly symmetric. All right? So remember then, that means that we have this bijection H, which sort of tells us that the basic open sets intersected with the subspace are exactly the images under H of the actual initial intervals in omega. All right? And what we can conclude is that if n is less than m, then this is this H function is sort of order anti-preserving, right? It's it reverses the order. And from that, right, what does it mean? It means that this is descending under the partial order. Actually ordered, and the numbers are actually ordered, then the images are is descending, right? Okay. All right, so how do we prove this? So suppose we have n less than m, and let's pick any open set U containing HM. We'll show that HN is in there as well, so that then we will see that HM is in the closure of HN. Okay? So here's an open set U containing HM, so it's some basic open set. And then therefore, since this is the initial segment topology, right, there's some J so that U intersect Y is exactly the image of the numbers less than or equal to J under H. Right? That's exactly what the initial segment topology tells us. All right, so, well, since H of M is in here, that means M is less than or equal to J. H is a bijection, right? It's 1-to-1. And N is smaller than J, so also H of N is in here. Does that make sense? So what do we conclude? We conclude that H of N is in the closure of H of N, so H of M is less than H of N. That's the previous fact. All right, that's the proof. Okay, so we, just to bring it back to the motivation, right? We have a topological theorem that we now realize is completely just a combinatorial theorem in disguise. Right? Okay, so that's this. Let's move on to this one, GSCL. So GSCL, we won't have a completely satisfactory answer to yet, but we will soon, and it'll sort of be previewed in the next slide. So in fact, GSCL is equivalent to GST1. So, and that might be a little surprising because GSCL is the full Ginsburg Sands theorem, except we don't care about the complexity of the closure operator. And GST1 is just that construction at the end of that inductive construction, the T1 case. But this is saying they are, in fact, sort of combinatorially, they are the same. Right? Okay, so how do we prove this? So let's prove GST1 implies GSCL. So we have a CSC space, and we have its closure operator in hand. Well, we'll do the proof, right? We'll go back to the original proof. With the closure operator, we can define these two guys, like before, right? And that brings us to that situation where we have a partial order. And now here's the thing where, unfortunately, I have to reveal my hand, right? The reveal of what's coming, which is that what we're going to show is that GST1 implies Ramsey's theorem for pairs. Ramsey's theorem for pairs implies CAC, which implies ADS. So now we can just finish the proof, right? We can apply CAC, ADS, get to the T1 case if necessary. And if we get to the T1 case, then guess what? We have GST1. GST1 can handle the T1 case, right? Not necessarily by the inductive argument, just does it however GST1 wants to do it, right? GST1 knows how to solve the T1 case. So this will be a focus for much of the rest of the lecture. All right, let's do the reverse. So GSCL implies GSCL. So let's consider we have a T1 CSC space. In a T1 CSC space, the closure operator is trivial. Right? The closure operator only contains the point. Closure of X is X. Yeah? So trivially, this X is an instance of GSCL. Okay, let's apply GSCL, and now let's think, all right, we have a T1 space. So when we apply GS, okay, GSCL, but since we have the closure operator, we're applying GS, really, right? It can't give us an indiscrete space, because it's T1. It can't give us an initial segment topology, because it's T1. It can't give us the final segment topology, because it's T1. So what does it give us? It gives us either a discrete subspace or something with the cofinal topology, which is exactly what GST1 wants as a solution. So we get it back. Any questions on this? All right. Okay, so we understand now, we understand this guy, and we understand this guy. We now understand the situation where you don't worry about the complexity of the closure operator. And we see that, we saw that this and this are the same, so we still, we have to understand this or this, right? We have to come back to that, so we will come back to that. But that leaves this guy and this guy, right? The full theorem and the theorem without worrying about the T1 case. Okay, these two are next. All right, so we're gonna have to do a little work to get to that, but now, of course, we have to worry about the complexity of the closure operator. So the first thing we might notice, and this is not so surprising, is that the existence, just in general, saying the closure operator exists, building the closure operator, that requires AC naught. AC naught is sufficient for it, but in fact, in general, it requires AC naught. That's the kind of thing that, like, once you do enough reverse math results, this is going to happen, right? Like, it cannot not happen, right? So yeah, so just for fun, let's do it. So let's assume that we have the statement for every CSC space the closure operator exists. That's a principle, right? So an instance is a CSC space, a solution is the closure operator. And we want to prove AC naught, so what are we going to prove? We're going to prove that ranges of functions exist. So here's a function from n to n, let's prove its range exists. So here's the lovely way to do this, right? You define this for every x, you define infinitely many sort of subbasic open sets, VXS, and what they do is they contain 2x and 2x plus 1 normally, right? Until if ever, until if ever you see that x is in the range of f. Once you see that x goes into the range of f, right, it has to have a witness, something puts it into the range, some y. From that y onwards, you only make this contain 2x. Okay, so you have, now if you look at the CSC space generated by this, right, you're going to have a bunch of these things. Each one of them is only going to, for various x's, is going to contain 2x and 2x plus 1. And for those x's that are in the range of f, there's also going to be a bunch of just 2x's, singleton 2x's. In there, right? Okay, that's great, because now we can say that x is in the range of f if we have the closure operator, if and only if this is in U, right? Which, how do we say that 2x is in U? Well, that's a sigma 1 question. We can't just answer that. But with the closure operator, we can, because we can say, that means 2x is not in the closure of 2x plus 1. There's an open set containing 2x that doesn't contain 2x plus 1. Make sense? Okay. All right, so it's complicated to build a closure operator. That's the moral of that, right? So we might therefore anticipate where the full strength of the Ginsburg Sands theorem is going to be, and it's going to be at the level of AC naught, right? So we'll come to that in a sec. But I want to take a detour here because we'll need this in the proof and to introduce an important concept that shows up a lot in the study of these kind of combinatorial statements, and that's this bounding schema. So the bounding schema are just sort of induction first order principles that are that sort of nicely complement the induction hierarchy, right? So what does the induction schema say? Suppose we have a gamma. Gamma is a class of formulas, sigma 2, sigma 5, whatever. And the gamma bounding schema says the following. So for each formula phi, we're going to have an axiom that says, okay, for every n, if each of the numbers x less than n has a witness, so that that formula holds of x and that witness, then we can bound all the witnesses for all those numbers less than n. For each number less than n, there is something, well then there's n many somethings, right? So I can put an upper bound on them. That seems like a very trivial thing to do, right? But in fact, it's an induction principle, right? It requires some work to do that, right? You have to sort of think about, well, how would you actually prove this, right? If you sort of think about it. Well, you might say, well, let me pick the least one for which it doesn't work, something like that. And you very quickly arrive in kind of induction territory, right? And indeed, that's the case, okay? So here's I sigma 1, which remember is the amount of induction that we have in our CA naught, in our base system. And then B sigma 2 is above that, right? Which is below I sigma 2. B sigma 3 is above that, which is below I sigma 3. So Kirby and Paris give us this nice hierarchy, right, of this intermingling of the bounding and induction schemes. And it's worth knowing that B sigma 2 and B pi 1, B sigma 3, B pi 2, we have that equivalence. And basically that's because the sigma 2, you can subsume the existential quantifier into this quantifier, right, leaving you just with the leading universal quantifier there. All right, here's how this connects in a beautiful way to combinatorics. This is one of the most just delightful theorems, I think, right? So this is telling us that B sigma 2 over our C naught, B sigma 2 is the same thing as Ramsey's theorem for singletons. And remember I warned about this yesterday, right? That when you're talking about Ramsey's theorem, without fixing the number of colors externally, like to 7 or some standard value of 7, then the number of colors could be infinite, right? I mean, in the real world, right? It could be some huge number, except in the model it looks finite. Okay, so for all KRT1K, this principle, where this is being quantified internally, that's B sigma 2. It's a beautiful theorem, and it has a beautiful proof, and you can try to prove it, and it's a doable proof. You can think about it, right? In one direction, it just comes from B sigma 2, and the other, once you figure it out, it's very beautiful the way it works, right? So you have to think by contraposition. It's wonderful. Okay, so these are some kind of useful things that we're going to use moving forward. Okay, any questions just on this? Okay. What else are we going to need to know? We need to know that CAC implies B sigma 2. In fact, more is true. ADS implies B sigma 2. But that's a harder proof, so I'm not going to do that one. And I don't need it. So we'll just do CAC implies B sigma 2. I think it's a nice example of how you can prove B sigma 2. Right? So let's prove it. Since the tutorial, let's prove it. So how do you prove B sigma 2 from CAC? Of course, you're not going to prove B sigma 2. Right? Once we have Hurst's theorem, we never want to think about it. We think about it instead of as for Ramsey's theorem for singletons. Okay, so we're arguing in our C naught, and we fix some K, which may be non-standard, and we fix a coloring. Okay, so we have to be careful, right? We can't make flawed arguments about K that rely on standard properties that may not be there in these kinds of arguments. All right, we're going to define a partial order, so we're assuming CAC, right? And we define it as follows. We're going to say x is p less than y if x is less than y, and they have the same color. It's sort of the most obvious coloring you might, partial order you might think of. And it's a partial order. You can check transitivity, right? So if you have x, p less than y, p less than z, then x is less than y is less than z. And these two things have the same color, and these two things have the same color. So these two things have the same color, and therefore x is p less than z. Right? Okay, so it works. Right? It's good. All right, so it's a partial order, so we can apply CAC to it, and we get some infinite set like this, which is a chain or an anti-chain. Okay, let's suppose it's a chain. Then what do we have? We have that x0 is p less than x1 is less than this. That means they all have the same color. That's an infinite homogeneous set, which is what RT1 wants. Suppose it's an anti-chain. It might be an anti-chain. Well, it actually can't be. And the reason is that what happens then, that means that CXI is different from CXJ for any two of them, right? For any two elements in here, right? Because they're incomparable, so that by definition, they have to have different colors. Okay, and now's the kind of situation where you have to be very careful, right? Because you might sort of say, well, then that's too many colors or something like that, right? Well, how do you actually prove that carefully? So you can pick k plus 1 many of them. And that gives you k plus 1 many different colors. But C takes each of these to a color in k, right? So that gives you an injection from k plus 1 into k, which you can interpret as a finite set, right? And using I sigma 1, you can quantify, you can just prove that, you prove for every number, if you interpret that number as a set of pairs, that thing is not an injection of a larger number into a smaller number. That you can prove by induction using I sigma 1. So that's okay. But it's that kind of level of granularity that you have to have with these kinds of values. I assume Kata and maybe Anton will say more about the dangers of some of these things. Anyway. All right, so now we can go back to our main theorem and prove this result. Okay. So we want to prove that GS and in fact WGS are both equivalent to AC naught. Okay, so we already know AC naught proves GS. That's our first slide today. And GS, of course, proves WGS. WGS is just a restriction of GS. So we just prove WGS implies ACA. And we're going to, of course, prove that the range of a given function exists. All right, so let's use this notation here. Range of f up to W in x steps. Right, so I think hopefully it's clear what I mean, but I just mean it's the range of f up to W, right? Which as we see it, if we only look at the values of the function on things less than or equal to x, right? So anything in the range has a witness for being in the range, and so we're looking at all the things in the range that are less than W that have a witness smaller than or equal to x. Is that okay? So you can sort of think, right, that if you're thinking computability theoretically, the range, of course, is a CE set. So really, we're sort of thinking this is the set of elements less than W that have been enumerated by stage X, right? Okay. We're going to do the same kind of thing. We're going to define some fancy sub-basic open sets. So in this case, we're going to set VXS to contain X, so that X is in there, and then numbers smaller than x, and this is important, so VXS can only contain x and otherwise numbers smaller than x, so we'll come back to that later, such that what? Such that the range up to W does not change between stages x and x plus s. So between here and here, no new numbers come into the range f below W. That make sense? So it's looking, good. If this S could, for example, go arbitrarily large, that means this is the true range F up to W, right? All right. So again, these are the sub-basic open sets. We do this kind of canonical delta 1 procedure to generate the CSC space out of that by closing these things on the intersections and defining the K function appropriately. And now we're going to prove a couple of claims. One, for every W, X belongs to the closure of W for cofinitely many W. For all sufficiently large W's, W belongs to the closure of X. For all sufficiently large X, X belongs to the closure of W. Right? So you fix a W, and I want to say, okay, almost everything belongs to its closure. That's already very much restricting, right, what kind of topological space this is. Right? All right, so how do we prove that? Okay, so here seems to be a completely innocuous statement. We're looking at range F up to W for some fixed W. And I'm going to say, okay, well, let's take an X big enough so that this is correct. Right? Well, that's a problematic statement, right? If you sort of think about it on its face, because what do we know? We know that for each number smaller than W, either it's not in the range, right? Which is a pi1 fact, or it has a witness to being in the range. Yeah? So we can reformulate that. We can say for every number smaller than W, there's a witness such that either it's not in the range or that witness is a witness to it being in the range. Does that make sense? Okay. So that's an example of, that's an instance of B pi1. Right? Because I'm saying for every x smaller than W, oh, sorry, I shouldn't say x, for every number smaller than W, there exists something pi1. And I'd like to pick an x that works for all the numbers up to W. Now I'm using B pi1, which is to say B sigma 2. Right? There's B sigma 2. Okay, but that's okay. This proof is happening in WGS. WGS implies WGSCL. WGSCL was equivalent to CAC, and CAC implies B sigma 2. Okay, so we're good. We can use B sigma 2 all we want. All right, so that's why we needed it, right? Okay, so now what do we have? We have this, so we're good there. And let's just note, right, that the claim is that this X and anything larger than it belongs to every open set containing W, right? So what do we have? We have, let's look at this X. What are the kind of basic open sets? Where are the open sets built out of that it can belong to? Well, it's going to be some things like this, right? Every open set is an intersection of these kinds of things, right? These basic open sets. So maybe X is in VXS. Well, okay, if it's in VXS, it's in there for all S, but also W is in here, right? Because first of all, W is smaller than X, and, right, we cannot change, the approximation of the range of F up to W cannot change between X and X plus S because X was already the point at which it was correct. Does that make sense? Right? So, okay, so here's a particular open set containing X, and we just showed that W is also in it. Remember, we're trying to show X is in the closure of W, so every open set containing X should contain W. All right, let's suppose we have some other kind of open set containing X. All right, so now let's think of something VZS for some Z bigger than X. Right? Remember, it can't be smaller than X, right? X cannot be in an open set unless it's smaller than whatever this index is, right? So X cannot be in VZS for any Z smaller than X. All right, then what do we know? Then we know that the range of F up to X does not change between Z and Z plus S. That's what it means to say that X is in VZS. Well, W is smaller than X, right? So if the range of F does not change between these 2 points up to X, and it certainly doesn't change up to W, right, because it's smaller, so W is in there too. And that proves the claim. Okay. So we have this, right? For every W, there are cofinitely many X such that X is in the closure of W. Okay. Where do we use that? We use it right here. So we're going to apply WGS to the CSC space, and we're going to think a little bit about what kind of CSC space this can be. It can't be T1 by this fact. In the T1 space, this does not work. Yes, please. What was the it says indiscrete, initial segment, final segment, or T1. Okay, so it cannot be T1. That's what we're eliminating the possibilities, right? So that we know what it is. Okay, good. Yeah, thanks for that's a good reminder. Okay. Also, what do we have? If X is less than Y, right? Then this thing contains X, but not Y. Remember, Y has to be smaller than X, right? So Y cannot be indiscrete. Their points are separated, right? This is a T0 space. It can't be T1, but it is T0. So it can't be indiscrete. So that means we either have the initial segment topology or we have the final segment topology. Does that make sense? And so I guess it cannot have the final segment topology for the same reason, right? For this same reason. If you have the final segment topology, right? You take any point, cofinitely many things do not contain this point. Does that make sense? And this is exactly the opposite of that, right? So it can't be so it's quite asymmetric, this proof, which is sort of unusual, right? It cannot be the T1 topology. It can't be the final segment, and it cannot be the indiscrete. So since this is WGS, the only thing left is the initial segment topology. Make sense? All right. Okay. So here's our witnessing bijection for this to be the initial segment topology. So what does that mean? It means every open set U in the subspace topology, right, in here, has the form H of I less than or equal to J for some J. right? It's literally the image of a initial segment, finite initial segment. Okay, and the claim is that, okay, if we look at this y and we enumerate its elements y0, y1, the only thing H can do is just list out the elements. It can't jump around in the natural order, right? H of 0 has to be the least element, H of 1 has to be the next largest element, and so on. It's the only possibility. So this is a very nice kind of order preserving bijection, right? In this sense of the natural enumeration of y. Okay, so how do we prove this? So suppose not, right? Suppose we have n less than m, so that this is reversed. H of n is bigger than h of n. This is the normal natural order, right, on natural numbers. So suppose we have this reversal. So we can choose a j so that this open set VHM0, right? VHM0 intersect y is h of I less than or equal to j, right? That's every open set in the subspace topology has that form. This open set contains h of m and a bunch of numbers smaller than h of m, right? In particular, it cannot contain h of n because h of n is bigger. Does that make sense? This point cannot be in here, right? But h of m is in here, so m is less than or equal to j, and n is less than or equal to m, so it is in there, right? And that's the contradiction. So in fact, n less than m must imply hn less than hm, and now you just by induction can prove that h of n is equal to 1. You don't have any room. It has to be order preserving, and then that only leaves, since it's a bijection, it has to map least to least, next least to least. That you can prove with I sigma 1. Okay, so that's our second claim. All right, so we're almost there. So here's our second claim. What does that tell? Why did we want to prove that? Well, the whole reason we wanted to prove that was that, okay, so here's y, right? And the open sets, therefore, are, singleton y0, y0 to y1, y0 to y2, y0 to y3, right? Those are the open sets in the subspace topology in y. And in particular, all we really care about is that they're closed under less than. They're closed downwards on the natural order, right? So if we have any u and u, and we have 2 points in y, one smaller than the other, and one of them is in u, then the smaller one is in u. That's the key fact we're going to need. I mean, it's just h0 to hn, right, for every n. Those are the open sets. And using that, we can prove that the range now exists. How do we do that? So let's fix w, and let's prove that we can compute if you like this, right? That we can give a delta 1 definition of the range f up to w. Okay, if we can do that for every w, then of course we have the range, right? It's delta 1 definable. All right, so the claim is the following. We fix w, and then we fix x and z and y in this particular subspace that we got, which are larger than w. It's an infinite subspace, so of course we can do that, right? w might not be in there, but there's at least two elements larger than it in there, right? And the claim is that the range f up to w is the range f up to w with run for this larger amount, z steps. Suppose not, so then we can pick an s so that the range of f up to w changes between z and z plus s. Right, that's what it means to say. Then what? Then the range of f up to x changes between z and z plus s, right? I mean, x is bigger than w. But that means that z, like if we're looking at the z, we look at VZS, that open set. Remember, this contained z, this guy, and it contained all those things smaller than z for which this does not happen, right? So in particular, it does not contain x, but x is smaller than z, right? And we just argued that open sets are all closed under these initial segments. That's the proof, right? So that's how we're extracting the range out of a topological principle. And what I find interesting here, just as a quick comment, right, is that going into this, I guess my collaborators in the audience can say what they thought, right? But I really expected that this proof, I thought this proof would probably happen, but I really expected this to be using the closure operator. Because the closure operator is equivalent, the existence of the closure operator is equivalent to AC naught, and somehow you're going to do that. But it doesn't, right? It doesn't use it at all. In fact, it uses the initial segment topology in this rather strange way. That's surprising, right? So you get these interesting kind of windows on peculiar interactions that are underlying all this. Okay. Questions on anything? All right, so in the remaining time, then I want to now pivot to what remains, which is of our analysis, which is GST1. Right? So GST1, again, this is now just Ginsburg Sands for T1 spaces. So we're dealing with only two kinds of solutions, discrete or cofinite topology. Those are the only two possibilities. And we already know that morally speaking, or at least by someone's morality, that is GS, right? Unless you sort of are happy with it already being equivalent to ACA naught, and then you're done, right? I mean, there's nothing else to talk about. If you're not happy with that kind of picture, then GST1 is GS, right? Because the whole reason sort of it was there, or at least definitionally the reason it was there, was because of that closure operator, which GST1 does away with, which GSCL does away with, and that's equivalent to GST1. So there's good reason, right? There's independent reason to think of GST1, not just because it's the one that's left over, but because modulo the arithmetic complexity of the closure operator, it is the full Ginsburg Sands theorem, right? Which is what we're interested in. Okay. So as before, now I'm going to switch to combinatorics, and in particular to thinking about Ramsey's theorem, and do some review of things that some of you might know, some of you might not, right? But as to think about Ramsey's theorem for pairs, and in particular, a fruitful way that Ramsey's theorem for pairs was studied over the last 20, 30 years, and indeed, most of the combinatorial principles that this kind of study of combinatorial principles in reverse math and computability has involved, which is to look at not the full principles, it's too complicated, but to look at sort of decompositions of those principles into somehow better behaved versions of those principles. And what we call that stability and cohesiveness. And for Ramsey's theorem, right, it takes the following form. So suppose we have a coloring of pairs. Everything will be a coloring of pairs now with two colors. The number of colors, if it's standard, doesn't matter right over our CNOs. We're going to say that's stable if, right, for every x, so you have x and you color it red with this and blue with this and red with this and blue with this. And eventually it's all blue, 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 or red, 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 right? So for every x, there's a color such that for almost all y, cxy is equal to that color. Right? And we'll say that x has limit color I, right, in that case. I is the limit color of x under that coloring. So here's Ramsey's theorem for pairs. Every coloring has an infinite homogeneous set. Here's stable Ramsey's theorem for pairs. Says every stable coloring has an infinite homogeneous set. It's a different principle, but okay, you might perfectly understandable. Here's a slight variant of it. Suppose that instead of asking for a homogeneous set, I just wanted an infinite set of elements that have the same limit color. It's not necessarily homogeneous, right? If I have an infinite homogeneous set of color red, then every element inside that makes the color red with infinitely many things. So its limit color has to be red. Yeah, does that make sense? Since it has the same color for cofinitely many elements, infinite implies cofinite, right? And stability. Okay? So here I don't want that. I just want to have the weaker form, which is that all the elements inside this set have the same limit color, but maybe this one makes red with this one, blue with this one, red with one, and then eventually it's red with everything else. Okay, so we call such a thing limit homogeneous, not homogeneous, but limit homogeneous, sort of in the limit. And we notice, right, that if you have such a set, you can computably go through that set and thin it, right? Thin it out to so in the real world, right? You can go ahead and computably thin it out to a homogeneous one. Yeah, does that make sense? So long as you know the limit color, right? If everything limits to red, you pick the first element, you go down here somewhere, you find something that is red with it, because you know eventually everything is. Now you go down here something that makes red with both of these, right? You know both of them have the same limit, so you can do that, right? Of course, that's much more complicated in the reverse math setting, right? Because somehow you're picking something constantly going through, right? It's much more complicated. And in fact, so D22 is the statement every stable coloring has an infinite limit homogeneous set. Over omega models, the argument I just gave that these two things are equivalent is straightforward. I mean, that argument works. It actually is a non-trivial proof over arbitrary models of RCA naught. To show that you can do that with I sigma 1 is fairly sophisticated. It's this paper of Chang, Lemp, and Yang. Okay, but it is true. They are equivalent. A priori, you might think you need B sigma 2 or something like that. But in fact, you don't. Okay. So why is this useful? Well, suppose we have a stable coloring of pairs, then we can sort of think of these. Yes, Andrea. If I mean, in this setting, it doesn't matter because it's just logic. But in the Weirach degrees, you could have two versions, right? You can have like D22 or you can have D22 plus or C, whatever, where you have both, yeah. But here you would just say, okay, there is a color, right? So yeah, good question. Yeah. Okay, so we can think of stable coloring as inducing a coloring of singletons via this limit color, right? So if I have this stable coloring C, then I can say, okay, D is defined on the natural numbers by D of X is the limit color of X. And the point of this, of course, is that the limit color is not something you can know computably. You know it in a delta 2 way, right? Okay, so delta 2 way because there's a point after which it has the same color, that's sigma 2, but also infinitely many numbers have the same color since there is a limit. Again, infinite implies cofinite, right? Does that make sense? So we have both a pi 2 and a sigma 2 definition, and so this D is delta 2 definable from C. That's in RCA naught. There you can just write it down. So we have this delta 2 definable D, but because RCA naught does not have delta 2 comprehension, in general, this induced coloring it only exists as like a class function for RCA naught, right? It exists as a formula, not as an actual function, not as a set. And conversely, right, if you give me such a formula, a delta 2 formula, I'm saying delta 2 formula, but everybody knows what I mean, right, by delta 2. Give me a delta 2 definition, if you like, for a function which has this property, right, it's just a function of a 2 coloring of the integers, then I can define in a delta 1 way, and therefore provably in RCA naught, a stable coloring of pairs that has this property. And that proof is just Schoenfield's limit lemma, right, which RCA naught can prove with no problem. Okay? So that's how you go back and forth, right? So that if you want to summarize those two facts, you can sort of say that D22 is RT12, right, because I've gone from a coloring of pairs to a coloring of singletons, but modulo a jump, right, because I go from a computable coloring to a delta 2 coloring. And a slightly different way of thinking of this, which will be useful later, right, is that we have this strong correspondence, and really it's the same thing. On the one hand, we have this problem. Given a stable C, let's say computable or it doesn't matter, what are the degrees of the infinite homogeneous sets of that stable coloring? That's one question. Here's another one. Given a delta 2 set A, what are the degrees of the infinite subsets of A and its complement? Right, if you think of this coloring here as being a delta 2 coloring, you can think of the places where it's 0 as defining A, and the places where it's 1 as defining A, and the places where it's 0. It's the characteristic function of a delta 2 set. Okay, so these are the same question in this. Okay? So we move combinatorially to a simpler problem from Ramsey's theorem for pairs to Ramsey's theorem for singletons, which is a lot easier, right? It's a pigeonhole principle, but at a computational cost. We've gone up in complexity from computable to delta 2. Okay. What's the kind of the other side of the coin is cohesiveness. So suppose you give me a sequence of sets. These are just sets of numbers here, and I think of it as a coded sequence, right? Rn. We'll say that a set is cohesive for this sequence, or just are cohesive, if for each one of these Rn's, either the intersection with X with Rn is finite, or the intersection of X with the complement of Rn is finite. Right? So if you want, X is almost contained in Rn, or X is almost contained in the complement of Rn. But it can be different between the different Rn's, right? So almost contained in R0, almost contained in the complement of R1, almost contained in the complement of R2, right? and so on. Co is the statement that every sequence like this has an infinite R-cohesive set. Instances are arbitrary families of sets, and the solutions are the infinite R-cohesive set. And this one, maybe it's not so clear why this is true even, right? But it's not hard, right? I mean, you have R0, it's infinite, or its complement is infinite, right? So commit yourself to building in one of the two, which is infinite. Now, whichever that is, its intersection with the next one is infinite, or its intersection with the next one's complement is infinite, right? Now build only in that, right? Does that make sense? And you only have to do this. Oh, this should be a superscript, and a superscript which is missing there. Okay, sorry. Almost contained in. This is not all the way contained in. Sorry, I said it, but so you can start building inside, say R0, right? And you're building in R0, and maybe the intersection of R0 with R1 is finite. And all those points you picked in R0 were in R1, right? Now you switch to building inside R0 intersect R1 complement. That's infinite. There's going to be finitely many errors, right, where you were not in the complement of R1. But that's okay. This only needs to happen up to a superscript of a star here, right? Up to finitely many. All right, so that gives us, that's the standard construction of a cohesive set. All right, so why is this a useful principle to think about? Let's think of each of these Rn's as an instance of RT1, 2. Just by think it's a set, so we can think of its characteristic function, right? Then what exactly is a cohesive set? You have one coloring, you have another coloring, you have a third coloring, fourth coloring, you have infinitely many colorings. And a cohesive set is something which is simultaneously homogeneous for all of them. Right? It's homogeneous with color 0 for this one, homogeneous with color 1 for this one, color 1, color 0, but with finitely many errors. Right? So it's almost homogeneous, almost homogeneous, almost homogeneous. Does it make sense? So again, we've reduced co can be sort of thought of as somehow, going from the problem of RT22, although it's less clear here how it connects to RT22, to RT12, which is combinatorially simpler. But these finite errors, are difficult to detect, right? If you actually needed to detect them all the way across, you couldn't do it, right? Because you don't know, is this going to be homogeneous with color 0 or color 1? I see some 0 and 1, 0 and 1. I know eventually it's only zeros or only ones, but how do I know that in a computable way? There's some complexity issues again. The reason this is nice is because the SRT22, you like this kind of RT121 jump up, and co, if you like sequential RT12 with finite errors, they decompose the full Ramsey's theorem for pairs. Right? So if you want to know this, understand this, which we do, it's enough to understand this one and this one separately, right? And they are combinatorially simpler statements. And I guess as computability theorists, we don't know combinatorics that well, so we want to make that simpler, even if the computability gets harder, right? That's okay. All right, so how do you prove this? This is a nice proof. And I think that I'll end with that today. So suppose you have this coloring of pairs. So first of all, we can define a family of sets as an instance of co by Rx is all those y's so that the color of x and y is 0, right? Okay, that might be an infinite set, might be a finite set, I don't know, but let's apply co to it to get an infinite R cohesive set, x0 less than x1, blah, blah, blah. Then what do we know? If x is almost contained in Rx, then Cxy is equal to 0 for almost all y and x. Right? Almost entirely inside that set of places where it's 0. Right? If it's almost contained in Rx complement, right, then Cxy is equal to 1 for almost all y and x. Okay, so what does that mean? That means if I take my original coloring now and restrict it to this set, I have a stable coloring. So now we can define D, well, okay, if you like, you can define it directly on this and apply sort of SRT2 to relativize to this set, or you can do this kind of thing, right? So you're actually doing it properly. You're defining it on the natural numbers, and 2, you say D of NM is the nth element with the mth element in here, right? So that gives you a coloring. You get an infinite homogeneous set H for D by stable Ramsey's theorem for pairs, and now you take the positions of the elements corresponding to the positions in this set, and that's homogeneous for C. Okay, so SRT22 plus co, these two somewhat simple kind of problems, right? together give you full Ramsey's theorem. All right. In the other direction, okay, so let me go through this. So okay, RT22 implies SRT22. That one we're okay with. So we have to prove RT22 implies SRT co, right? RT22 implies co. Okay, so instead let's prove ADS implies co, because it's a better theorem, and it actually is a better proof. So the actual proof that ADS implies co is a result due to Hirschfeld and Short. It's a nice proof, but it's not particularly intuitive. And this is a much more recent proof that Alberto Marcone came up with that I like very much. So what you do, right, is you take, let's imagine the instance of co as a bunch of columns like this. You take them and turn them like this. So now they're a bunch of rows. You wouldn't think that's so dramatic, but it's really nice, okay? So we define a new instance as SVEC, where SI of n is Rn of I, okay? And now we're gonna do some case analysis. We're gonna say, hey, is there a row, is there some SI, so some row in here that occurs at infinitely often in S, right? So what does that mean? That means, so maybe I can draw a picture. Is there some chalk here I could use? Right, here, I see it, very good. Let me draw a picture here. Right, so we have these rows, right, and we've said that maybe this one here, S2, occurs at infinitely many positions, right? So what does that mean, right? So S2 has a 0 here, a 1 here, 0, 0, 1, 0, right? If we're thinking of it as the sort of the characteristic function of a set. So that occurs at, at infinitely many positions, the exact same pattern. And so what can you do? Well, you're going to say, okay, so I know S2, this is a fixed column of this set, and I know that this occurs infinitely often in here, right? So if I look back at my original instance of co, which now goes this way, right? What we've said is that, okay, so that means this particular pattern, right, is infinitely often down the line. Yeah? And so what I can do now is I can just say, okay, so let me start building indices of elements that are agreeing with this particular S2 on larger and larger initial segments. So I see an element over here, S14, and it has a 0 here, as this one does. I put 14 into my set, right? But maybe it has another 0 here, so eventually that's not particularly good, but then, okay, I find another one here, S27. It has a 0 and a 1 and a 0, so I put 27 in my set, right? But as I keep going on, I find all the infinitely many columns that occur in here as well, and the resulting thing is in fact a cohesive set, right? It's all the j, so that for all initial segments up to j, these two rows agree. So you can check, if you want, just that really works out very nicely. If we don't have this, if no row occurs infinitely often, then what can we do? We can define a linear order by just looking at the lexicographic order on the rows, excuse me. Because now they differ, right? So there will be a lexicographic order. They are lexicographically distinguishable, right? Each row is different from another row somewhere, right? And the point is that now I can just take an infinite ascending sequence for this using ADS. And the key is, okay, so I have this, which is lexicographically less than this, is lexicographically less than this, right? Well, all of these bits come to a limit, right? Lexicographic order in this first position, either it stays at 0 or eventually it switches to 1, and then it's a 1, right? And that happens at every single position. So that's exactly to say that this limit of each one of the elements in here, these columns, that limit in every single position exists, right? This value stabilizes, this value stabilizes, this value stabilizes, right? Well, if you flip it back, that's saying that this limit exists, and that's exactly cohesive, right? That's saying that eventually you're either in the set, you're out of the set. Okay, so that's the proof that ADS implies co, right? And in particular, RT22 implies co as a result. The reason I like this proof is it avoids a lot of these induction issues that are present in the original proof of RT22 implies co. You have to actually be somewhat careful there. But this proof is much more direct. Okay, so we're going to stop. We're going to stop here today and pick up with stability for topological spaces tomorrow.